Is everyone from the panel here? We have, I see Chelsea, I see Subotai, and we have Chris.
Yes, I see him.
Okay, perfect, cool. All right, so hi everyone, welcome to panel number 2. Thanks for the panelists for coming. So the rules of the game, just if you have some questions you want to ask to the panelists, you can write them in the chat. And if you want to ask them yourself, just say it in the chat. Just say, yeah, just mention it, and we'll unmute you, and you can ask them yourselves. So I have a couple of questions for the panelists. If you don't ask questions, I will fill up the time with those. So let me start this by saying that this is sort of a dream team panel for me related to my research. In the last year, I've been thinking about continual learning, and especially continual learning evaluation and meta learning within continual learning, and modularity and compositionality within continual learning. And today we have Chris Cannon from the University of IRT, and also a senior AI scientist at Page. And Chris is the expert in continual learning evaluation, so that's just perfect. We also have Chelsea, which has done a lot for the meta learning field recently, so that's perfect. She is a assistant professor at Stanford. And we have Subotai, VP research at Numenta, so the expert in sparsity, and hopefully, personally, I think this is related to modularity and compositionality. So this is why, for me, this is the dream team panel. So if anyone wants to ask a question, just go into the chat. But right now, there's nothing, so I will just start with some of my questions. And I will start with my favorite one, which is really open-ended. So basically, we humans, we can solve really complex tasks, but our environment is full of these natural curricula that are leading us to solve these complex tasks. So before I can understand deep learning, I normally learn about arithmetics, then maybe linear algebra, then probability, and then I can solve continual deep learning. So basically, my question is, does it make sense for us to study continual learning without this idea of curriculum learning? And if so, or if not, what would be a good way to study curriculum learning and continual learning simultaneously?
Well, hi everybody. I don't think we're really studying curriculum learning today in terms of continual learning. Now, does it make sense? Yes, I think it would bring a lot of value. I mean, from a developmental perspective, humans and animals kind of gain skills as they age, right? So we learn more things, we learn concepts, and we are able to utilize that information that utilize what we learn over time in order to presumably gain more efficiency at learning new things in the future. Today's systems aren't really tested on this, and but I think it makes a lot of sense. I think it makes a lot of sense to study curriculum learning in terms of continual learning, but today I'm not really satisfied with anything out there. My group has tried to do this a little bit in unpublished results, but everything was kind of a negative result. So we never saw any gains from anything we ever tried with using curriculum learning for continual learning to date. I still like the idea. I still think it has a lot of promise, but we haven't published anything on it because all of our results did not show any benefit from trying to do anything that we were looking at. We do have a couple curiosities in terms of curriculum learning with visual question answering, where we just kind of stumbled upon trying to learn different orders of the questions over time. And some of them seem to be much better than others, but I don't know if there's anything there right now.
Does Subotai or Chelsea want to add something to this?
Yeah, I can, maybe I could, since I come from a neuroscience background and studying things more from a biological perspective, maybe I can sort of reframe the question a little bit. You know, I think, you know, if you think about kind of mammals in general, they're extremely smart. What they do is, you know, they're constantly learning things. There's no concept of batch training. You know, you're getting a stream of inputs coming, you're constantly learning. And the key problem, and we talked about this in the afternoon panel earlier a little bit, I think one of the key problems that needs to be solved is, you know, some sort of getting more and more efficient transfer learning. That is, you've taken your entire lifelong history of what you've seen and what you've learned, and now the very next task you have, you are slightly better at it than you would be otherwise. And as you grow up and as you get more and more experience, you get better and better and better at it, to the point, you know, with humans, we can show you completely new objects and new tasks, and in one shot, you pretty much learned it. And as you get, you know, better and better at it, you're extremely efficient at learning the next new thing. And then the second part of it, I think, is an active mechanism where, you know, you're given goals and you have some internal goals or external goals, and you choose a set of actions to maximize those goals as efficiently as possible. And if you put those two together, you know, more and more efficient transfer learning in a continuous streaming sense, plus a mechanism for acting in the world, having predictions and achieving goals, I think you kind of get curriculum learning as a byproduct of that. And then you could say, okay, I want to be a machine learning scientist. What do I need to do to achieve that? Well, maybe I need to learn math, maybe I need to learn programming and so on. And then you kind of figure out and get better and better at it. So I kind of think of curriculum learning as something that arises naturally out of the first two things. And I think the real hard problem from a continual learning standpoint, one of the challenges we have is getting transfer learning to become incredibly efficient as you progress through, you know, your lifelong experience.
I also think that continual learning makes a lot of sense, or sorry, curriculum learning makes a lot of sense in the context of continual learning. And I'd love to see more proposed benchmarks around that as well. In general, I think that the continual learning benchmarks are lacking. I think that many times you see that we're doing continual learning on 10 tasks or 20 tasks, and that's a setting where you could actually do batch learning very practically, or just kind of keep on retraining after every single new task that you see. And I think it becomes a lot more interesting when you get to the setting where you have 100 tasks or 1,000 tasks. To Chris's point, I think that I also think that in general, with curriculum learning, it's very easy to get negative results where the curriculum doesn't actually help in comparison to just training without that curriculum. I suspect that one area where we may see a positive result, if we can actually develop a benchmark around it, would actually be in a reinforcement learning setting where the previous tasks are helpful for exploration for the future tasks. And if you have difficult tasks, you can make tasks like very, very difficult reinforcement learning very quickly by making the reward more sparse. And if you get to a point where the most challenging tasks in the curriculum have very sparse rewards or very difficult in that manner, then the previous tasks will help shape the kinds of strategies that the agent will use to explore and help give it an inductive bias of the kinds of strategies that are useful for that curriculum. So I'd love to see more benchmarks in the RL area.
Makes sense. Makes sense. Chris, can I ask what kind of experiments, what kind of data sets you use for your curriculum learning experiments?
We were looking at two different things, so we kind of stumbled upon this. So one was, so we all have, or at least many of us have tried to use replay as a method for mitigating catastrophic forgetting in systems. And so my group was looking at, we called it curriculum replay. And so it seemed clever. Let's try to come up with the right curriculum to do the replay, and this way we will get improved results. Nothing we found worked much better than random selection, but we pushed hard on it for a while. So that was one way in which we explored curriculum learning. I still think it has promise, but we haven't found anything yet. The other way was, which we haven't exhaustively explored at all, but we started doing continual learning for visual question answering, where the task is to have an image and then a string that asks a question about the image. And then we kind of stumbled upon some interesting results where a particular ordering actually performed very well on Clever. And I don't know if it was due to the curriculum or not. We didn't really, it was kind of like just a test, a curiosity. We're like, oh, we can also do this. We can also use this technology for VQA, not just incrementally learning object classes, very trivially. And then we saw this like giant boost with a certain order. And so maybe that was due to the curriculum, or maybe it was due to quirk, but we haven't really poked it right now. So I can't say anything concrete, unfortunately.
Okay, cool. Thanks. I guess before I jump into the crowd question, my first question is a follow-up question. So related to curriculum learning, life is full of these natural curriculas. And then there's also this idea of compositionality. So when I'm learning about arithmetics, then I learn about linear algebra and I reuse some arithmetics to do that, and then so on and so on. So my question is like, because we have these natural curriculas and we reuse our modules, let's call them this way, maybe catastrophic forgetting is sort of solved by itself because we keep reusing our modules over and over again. So we are not forgetting how to use these modules because we use them over, like I'm not forgetting how to add because I reuse my addition modules every day when I do deep learning, and so on and so on. So I'm wondering, this is related to the first question, does it make sense to study continual learning without these idea of like modularity or compositionality?
I think that there may be some problems that don't naturally have that sort of compositionality, while some may. For example, one situation that we've looked at is a robot that is a legged robot that is learning to navigate on different terrains, such as grass, gravel, carpet, styrofoam, that they're very different. And it's kind of continuously kind of adapting and learning as it encounters each new terrain. And that's an example where there isn't really any clear compositionality of the behavior that it should learn for each of those different terrains. I think they're just kind of a bit different. And if it encounters like a new terrain like ice, it should continue to learn, but it's not necessarily compositional from what it's learned previously. That said, I think there are absolutely situations where there is compositionality, and it does make sense to be thinking about that. Although it's not that doesn't mean that you necessarily need to build it into your algorithm itself.
Chris and Subutai, you don't want to add something?
I don't have a lot to add.
Okay.
I think compositionality is going to be really important for actually getting forward transfer to be effective. Because today, I mean, most of the system, I mean, a lot of systems problems are not compositional, but there are ones where you would expect to see some sort of forward transfer and compositionality to help. And right now, we don't see that much, unfortunately. And I think that's not necessarily a failure of the problems, but more of a failure of the algorithms unable to learn reusable concepts that enable that kind of forward transfer. Or maybe we're just setting up the problems wrong. I'm really not sure.
Yeah, I would totally agree with that. I think it's very related to the transfer issue, and deciding when something is compositional or not is just part of it. If something is compositional, it can reuse past knowledge efficiently. If you solve the transfer problem, you'll automatically solve that problem, I think.
Okay.
One thing I'll add in response to Chris is that I think that we have started to see some forward transfer, at least in the algorithms that my group and in the realm of meta learning works on. If the tasks are close enough to what you've seen previously, we've seen pretty positive results. And actually, the terrain problem that I was mentioning, we actually that's an example where we were able to learn to adapt to a new terrain with much less data than if we were to train from scratch. So I'm pretty optimistic about the forward transfer problem, and actually that's my core interest, less so than the backward transfer problem, because in robotics you could just store all the data that you have for most of the problems that we want and just replay it. And interaction with the world is much more expensive than computation and memory, and we can so I'm excited about forward transfer, and I think it's definitely something that we've been able to make some progress on, but more progress is always good.
Cool. Okay, I'll take a question from the crowd. So German is asking, what is the relation between continual learning and meta learning? So
I can take that. So I think that there are many different definitions of meta learning. So it's hard to necessarily, and also many definitions of continual learning for that matter as well, many different problem statements. But from my perspective, I like to think of meta learning as sort of a slice of the continual learning problem, where you assume that you have some past data and you want to be able to use that past data in a way that allows you to transfer to new tasks with a very small amount of data. So it's really kind of studying essentially the forward transfer problem in one slice of continual learning. And I think that we've of course developed some kind of online and continual meta learning algorithms that continuously perform meta learning throughout the lifetime of an agent. But meta learning of itself doesn't necessarily need to be in a continual learning setting. It may only be just one slice of that problem.
Mm-hmm. Okay. Let me take one from the crowd again. For a robotics application, which aspect is more promising for applying continual learning or meta learning? Perception, control, planning, or a subset of them? I'm not sure I understand exactly the question, but if some panelists understood it better than me, maybe they can answer.
I think the question is from Roger here. He can maybe ask it himself.
Oh, sure. If he's there and want to ask it, he can do it.
Hey, yeah.
Hi.
Hey, hello. So my question is actually for the robotics application, mostly we are focusing on the visual learning problems. So this related to the perception using the continual learning. But actually for the planning, such as some of the robotics traditional tasks, also some control from the robotics and manipulation, and also coordination between multiple agents. These are all robotics applications. So CL can apply to others. Besides the perception, we have seen a lot of experiments already done. I think Chelsea can help answer.
Yeah, so the like-a robot example actually that I mentioned, we weren't doing any sort of meta learning on the perception side. That was actually purely on the control side. And then we've also done it on very perception-heavy problems such as visual imitation learning. So in general, I think that meta learning and continual learning can be really applied to all of these things. I've also seen meta learning be used to speed up planning processes as well, to kind of essentially learn how to speed up planning, for example. So yeah, all of them would be kind of my answer. And I think that we should be thinking about bottlenecks in these kinds of in the applications that you care about, and try to figure out how transfer can allow you to increase efficiency and performance.
Cool.
Thank you.
Okay, so let me ask one that might be more related to Subotai's research. So it's back to compositionality. So I guess in the brain, from your video, we see that we have really sparse activation. So whenever I think about sparsity, I also think about modularity. So I'm wondering, do you think we can get any insight from neuroscience to get us to train these, let's call them modular neural network modular neural networks that are known to be really hard to train, but when they train, they can generalize very well. So if we could solve that, it would be nice.
So I could try. So I think in neuroscience, I don't know how much has been studied in terms of compositionality directly. But I can make a couple of points maybe related to my talk. One is, as you mentioned in my talk, I go through the sparsity of activations and connections in the neuroscience, how things are extremely sparse. And one of the surprising things that comes out of it is that these sparse representations are very stable, in the sense that they're very noisy. You can add, if you're recognizing some sparse patterns, you can recognize them under a tremendous amount of noise. without interfering with other sparse patterns that are also learned. So you can actually learn a tremendous number of representations that are provably far apart in representation space, so they don't kind of collide with one another, yet you can recognize distorted versions of each one. So when you think about compositionality, I think that's a core property you're going to need, is you'll need a representation system that is inherently stable and inherently robust to interference from other representations. So this allows you, it gives you a kind of a foundation to learn a bunch of new things that are sort of self-consistent but don't collide with one another. And in the talk, I used it to show how it can help with catastrophic forgetting, but I think it applies to compositionality as well. So I think sparsity could be a core kind of foundational piece that you could build compositional systems on top of. Yeah.
Cool, thank you. Okay, so another question from German. Do you think backward transfer is equally important as forward transfer? Could this make overall learning more efficient, for example, in terms of sample efficiency?
I think this really, really depends on your application. There are so many different applications and use cases of continual learning, from like medical data sets where you really care about privacy of data and you can't store a lot of data, to robotics applications, to like studying human learning, for example, and the constraints of your problem. In some cases, like if you really care about not like if you can't store data, for example, and you really care about computational efficiency, then avoiding negative backward transfer may be really important. Whereas in robotics applications, I tend to focus a lot on forward transfer because we can store a lot of data. We can use a lot of compute to keep on training on our previous data. And you may also be in a situation where it's actually good to forget something because you're not actually going to need it in the future. But I think it really depends on what your application demands.
Makes sense. Okay. Then let me ask a question to Chris. So I really enjoyed the talk. I'm really thinking the same way for continual evaluation with respect to compute. So I think it's a little bit weird to study catastrophic forgetting without mentioning compute in our papers, because you can solve catastrophic forgetting with compute. I'm aligned with you for task revisiting and so on. My only concern was this constrained memory thing. So for me, it might be a little bit an overkill to add memory constraints to our algorithms, because let's take the cloud argument. So you could give access to the cloud to your model, and because memory is cheap, you could, if you have enough compute, you could just access those old memories. So it feels unrealistic to put those memory constraints. Then from your video, you say that, okay, but there's these maybe embedded systems that don't have access to the cloud. But is that a big enough subfield into this whole continual learning field so that everyone should put constraint on their memory? Or what do you think about that?
Okay. So as Chelsea pointed out, she doesn't have a problem with using as much memory or compute as she pleases for her problems, which are essential. You know, if she's trying to actually get something to work right. I'm imposing constraints because for supervised learning, she's working on reinforcement learning. In the supervised learning world, at least based on my own papers, there's one that we published in ICRA, you basically can solve catastrophic forgetting. And there, other people have looked at this too. I mean, you can basically solve it. If you have unlimited memory, just progressively fine tune. You've solved the problem. Just keep growing your database and fine tuning it. Perfect. So unless you impose memory constraints, you're not really doing anything useful. I mean, in my opinion, I mean, unless you can see something that is like improving over, I mean, if you're doing something where you're demonstrating an improvement over an offline model, then maybe you're seeing something. But if you're saying, I'm just trying to prevent catastrophic forgetting, I'm trying to get the same performance as an offline model, Well, I can tell you how to do it. Use unlimited memory. You're good to go.
Yeah.
You're going to get, I mean, our paper showed to get over 99% of the performance of an offline model. We just did this. It's not scalable. We were able to do it for much smaller data sets, but I mean, that'll get you there. So unless you constrain memory in the supervised learning world, yeah, it's like we could solve it. It's not interesting.
I mean, so I agree with this, but I guess what I'm trying to say is, if you were to study models in, let's say, performance and compute space, which I think for me would make a little bit more sense because I think compute solves catastrophic forgetting, then in this case, you can remove the unlimited, the constraint on the memory and be closer to real life where you don't really have constraint on your memory and it's just about getting as good as possible with the compute you have.
You think we don't have limited memories? I don't know. I think
with the cloud.
I don't know if we have unlimited memories as humans. I mean,
because
my
of
memory is
the cloud.
very forgetful.
Sorry, I keep interrupting. So I'm saying because I have access to the cloud, I can just put everything on the cloud, and if I forget something, I can just go on Wikipedia or whatever.
You're not wrong. I mean, but to me, that's not really. So let's assume we wanted to only attack the compute problem and say constraining memory is not a useful exercise. I mean, that might be interesting if you could somehow do it. I don't know how you would constrain compute and do it in an apples to apples way to compare against the literature. I mean, what we've been doing is studying streaming learning, which is training one instance at a time and forcing a system to learn basically as one pass through the data set with a constrained amount of memory. And if we unconstrain the memory, it would still have to, and still assumed that we had some limited compute, then it would have to efficiently select what things to find in its memory. So it might be sufficient. I don't know. I'm not necessarily. I don't know. I'm not comfortable with it right now. You might be able to convince me, but I'm not comfortable right now.
Okay. Cool. I'll make better arguments and ping you in the future. Okay, so we have a question from to Subotai. So the talk by Subotai was very interesting. What are some of the limitations of biologically inspired unsupervised continuous learning system? So I guess the HTM-ish model.
Yeah, thanks. Yes, in the talk, basically what I showed is how you can build a very biologically inspired model that's learning continuously by making predictions about the future. And then when that input comes in, that becomes an error signal. You kind of learn from that, and then you make your next prediction. So it's a continuous unsupervised learning system. The limitations in that model, so in that model we trained using a very simple local Hebbian learning rule. So everything is completely localized as it is in biology. The big problem with that is actually solving the credit assignment problem. That's one of the big limitations that we are currently working on. So backprop through time would solve the credit assignment problem, but that's not really biologically feasible, and of course gets into memory limitations, which maybe there aren't any, I don't know. But so the question is that a really important question, I think, is how can you have local learning rules that are efficient, sample efficient, and still work in this predictive learning, but still solve the credit assignment problem efficiently. And we know that has to exist. The brain has to be able to do this, but that's still I think an unsolved problem. And there are several kind of researchers kind of working on that, but that's one of the big challenges that we face in our kind of HTM style learning algorithms.
Perfect. Thank you. Okay, I have one for Chelsea. Let me see if I can phrase that correctly. So I guess in research in AI, we study like these things in vacuums, so like vision ear and language ear. And the two things that seem to be normally studied in vacuums are learning on non-stationary data. So let's call this continual learning for now. And then credit assignment and control, which we study in reinforcement learning. But Chelsea, you seem to be like to research both of these things simultaneously in your papers. So I was wondering, do you think that more of the field should follow your footstep and study learning on non-stationary data and credit assignment and control simultaneously? Or should we continue separately and meet in the future when both are solved?
I do think it's really, I guess my perspective is that I really like trying to get as close as possible to, well, as close as possible to the actual problem that the end problem that you're trying to solve. I think that it's very easy to say, oh, I'm going to do this, like I'm going to try to solve this kind of intermediate problem and never actually bring that to the final problem. Like I'm going to study object detection for robots, but I'm never actually going to use that object detector for a real robot. And I think that the danger of that is that, well, it's not necessarily true that that intermediate problem is actually useful for the final thing. And I see all the time in computer vision papers like, oh, this could be useful for robotics, when it's not at all clear for me from a robotics standpoint whether it would actually be useful compared to other approaches that are more directly trying to solve the broader problem. So yes, I think that it's good to get closer to the, if you're interested in kind of the applications of something like a robot, I think it's really good to be actually looking at the control problem in addition to the it. And of course there's of course overhead associated with going to the final problem, like especially if you go to a real robot, for example. But I think that every once in a while touching that real robot can help inform what are the bottlenecks and what are the problems. And then that can inspire research. So a lot of the work that I've done on meta learning has actually been inspired by the work that I've done on robotics, because we didn't want the robot to be training from scratch for every single task that it's being trained to do. And actually that's a domain where fine tuning doesn't work that well. Although I showed some kind of positive results in my talk, but we haven't yet seen fine tuning to completely new tasks. And the goal of meta learning is to really try to accelerate that in comparison to fine tuning. We've seen some positive results there. So yeah, I think it's good not to assume that what you're working on is good for a final application. I think it's really easy to implicitly be like, oh, this is clearly like going to be useful. But actually touching the end application once in a while, not the end application in the sense of like the industrial robot, but the end application in terms of like actually what the like inputs and outputs would correspond to.
Thanks. That was a great answer. Okay, let's see. Okay, I guess this question naturally leads to another. So right now in continual learning, I would say like 99% of the paper do sequence of vision tasks. This has some advantages because it's like super standard and we know vision. But is it dangerous because maybe we're overfitting continual learning vision and we're missing out on some stuff? I'd love to hear you on this.
I don't know. I mean, so I don't know, maybe I'm biased, but my group has studied both learning in audio data sequentially, and we've studied multimodal data for vision plus language and VQA, more or less. And we have a paper under review for doing basically another vision plus text problem that's not VQA. But I don't know. Are we endangering ourselves by focusing on vision? I don't know. I mean, a lot of machine learning has made a lot of progress using vision, so I don't know if that's necessarily true. I mean, a lot of these things generalize pretty well. Vision has some of the best curated data sets, if nothing else. I would love to see more work in NLP for continual learning, but there hasn't been that much pure NLP for that. So I don't know, but I don't know if we're necessarily endangering ourselves by creating systems that won't generalize to other domains. Keep in mind that while the computer vision community and machine learning community has been really interested in this topic recently, under the name continual learning, but data mining community's been looking at this for lower dimensional signals to learn from all sorts of things, just because they have basically infinite data from the web or whatever. They've been studying this, so it's not like I don't think necessarily our solutions that we're developing are too specific and won't generalize because they've been kind of focused on vision.
Yeah, maybe I can give I agree with that. Maybe I can give a kind of a neuroscience perspective on this as well. One of the really fascinating things about the neocortex. So first of all, the assumption behind that question is that, if you specialize on vision, you're not going to do well on other domains because the underlying algorithms are going to be very different for different domains. So therefore, you're kind of specializing just on vision. That's kind of one of the assumptions in that question. So one of the really interesting things of the neocortex is that, and the neocortex is kind of the largest part of our brain. That's kind of where intelligence happens and does visual processing, auditory processing, planning, everything that we think of as intelligence. The neocortex is split into hundreds of thousands of copies of a specific microcircuit. And that microcircuit is actually remarkably consistent and independent of the domain. So whether you're doing visual recognition or auditory recognition or language or planning or almost any intelligent function that anything that's done in the neocortex, it's essentially the same microcircuit and the same algorithm, if you will, that's working on that. So you can use almost any of these domains to study continuous learning or these hard tasks if you kind of buy into this belief from the neuroscience that it's basically the same algorithm. You just, once you understand the algorithm, you can scale it to a really large system. So I think, sort of agreeing with Chris, it's not too bad to focus just on vision. I would say you have to incorporate all of the characteristics that and create sufficiently complex visual benchmarks to incorporate all of the different aspects. And, I think we both think streaming is a really important part of this, that things have to be streaming, but also incorporating action and sensory motor and the sensory motor loop, I think is incredibly important. And so if you stick within vision, but in a streaming context with actions and sensory motor stuff, I don't think you're hopefully in too much danger of pigeonholing yourself.
Cool. That was surprising answers for me, so I'm happily surprised. We have Vijay Verabhadran. I hope I didn't mess up your name too much. That wanted to ask a question. Is Vijay able to unmute?
I'm right here. Yeah. That was a pretty good version of my name. Actually.
Ah, cool.
Yeah. So this question is sort of general to all the panelists over here. And this is in some sense drawing parallels to this problem in neuroscience of trying to understand what kind of a model the visual working memory is doing, in the sense that we could think of it two ways, right? Episodic memory could either be the slot-based model where there's this finite capacity where we could store some amount of elements in each slot that we have, or we could have a more continuous representation wherein we could store relationships between multiple items, in the sense wherein we can basically have more capacity by encoding a continuous representation of all items or that's present in the memory. And in the same way, what's the panelists' sort of take on the solutions that are learned by deep networks to different subtasks in a continual learning setting? Is it possible that these deep networks are overfitting to task-specific solutions to these subtasks in continual learning, when we'd be sort of bottlenecked by the amount of capacity we have, as opposed to sort of tapping into these more generalizable solutions that have some commonality, that capture this latent similarity between these different subtasks?
I'm not 100% sure I understand the question. I'm sorry.
Okay, I should probably phrase it better. Essentially, there are these subtasks that are being approached in a continual learning setting, right? There's task 1, task 2, task 3, and so on. And the problem over here is to be learning all of these tasks without forgetting a different task and so on. So my question is whether these deep networks that we train on this continual learning setting are learning idiosyncratic solution strategies to each of these tasks, as opposed to capturing the latent similarity that humans would potentially learn while solving these tasks. And what is the sort of take on whether it is possible to understand deep networks, or in general, any learning model's solution to these subtasks? And if these models are sort of learning these shortcuts to, by capturing these idiosyncrasies that are present in each subtask, is there some form of regularization that one can use to basically drive these models to learn more generalizable solutions that capture these latent similarities? Was that better?
Yeah, I understand what you're talking. I understand. Yeah. I think what you're trying to get at.
Yeah.
And that's kind of, I think, core to what we were talking about in the earlier Q&A session or panel. And that's the notion of compositionality and forward transfer, actually getting something to go to generalize across different tasks and having some sort of retention of capability that's useful. So primarily, I think the focus of especially the computer vision community that's interested also in continual learning has been on just trying to overcome catastrophic forgetting and make systems not kind of perform as well as an offline system, despite not being able to loop over the data continuously. But as far as like getting the tasks to actually transfer or anything like that, we haven't really been focusing on that. And I think it's to our detriment right now. I think the meta learning community, and Chelsea can probably speak better about this, is doing some things that may be more in line with what you're mentioning. But right now, I think the focus of the computer vision community is just like, how do you, because my focus has been, how do we avoid catastrophic forgetting if we want to learn 1,000, 2,000, 3,000 category tasks and still have it perform as well without somehow losing a dramatic amount of performance. But the next level, and the next thing we need to focus on is how do we actually get some forward transfer from those tasks to see that since we learned all these initial things, we actually see that future tasks are easier to learn rather than worrying about just losing our capability on the earlier tasks we learned. So right now, we're basically trying to fix a problem that's kind of ridiculous in order to make progress. But what you're asking, I think, based on my interpretation, is how do we kind of capitalize on those earlier tasks to improve future ones? And right now, at least for the problems we've been studying in the computer vision world or just general supervised learning, I don't feel like we're there yet.
Another perspective on this question is, I think maybe comes from some of the results we've seen in multitask learning, just in the batch setting. I think that we've seen in a few, at least in a few different domains. I'm not sure if it's been seen in vision, but I know that we've seen this in natural language and in reinforcement learning in the past, where if you train on, like, say, a set of 10 tasks, sometimes training independently on those 10 tasks actually works significantly better than training a single network on those 10 tasks. And this suggests to me that the solution that's learned when you, it suggests to me that somehow the solution that you're learning when you do single task learning probably isn't the one that kind of synergizes with all the other tasks. Kind of like it's maybe more idiosyncratic in terms of what you were saying. And it also suggests that multitask learning is having trouble finding the more harmonious solution among the tasks. So I think it's a problem that is really difficult. We've started to study it actually because we were working on meta learning and found that when we did meta learning across broad task distributions, the bottleneck was actually multitask learning, not meta learning, because it wouldn't even optimize on the training tasks, let alone generalize to the test tasks. So I think it is certainly a problem. We have a little bit of recent work in a paper called Gradient Surgery for Multitask Learning that shows some signs of life and is actually able to outperform single task learning on the set of tasks that we test on. But it's still, I think, probably an open problem to actually get them to recover the harmonious solution.
I think that angle is the right one. I mean, I haven't really been working on multitask learning, but it's on my to-do list now. I think one of my PhD students who I was trying to pivot into this realm called in here. because I feel like just I've been working on continuous learning for a long time and trying to stop the catastrophic forgetting problem, but I think to gain more there, at least me personally, I need to start attacking multitask learning, offline or continual, doesn't matter, but in figuring out how do you enable multitask learning systems to gain from having those multiple tasks rather than, or when do they improve from having multiple tasks rather than a single task? I don't think that's really known. People have been studying multitask learning for actually a long time, and people are like, well, in this scenario, having multiple tasks helped. In this scenario, it didn't. There's no clear guidance on when you see a benefit versus you don't. So how do we get that working better is something that I'm personally interested in right now, and I'm hoping that will then feed into my continual learning research.
Thanks. To follow up on that, do you have any ideas of what kind of multitask learning we should do within supervised learning? Like, should it be like only vision task, or should we mix vision with language and graphs, or what kind of multitask do you have in mind, if you have something in mind?
The multitask learning that we've worked on recently has been in the context of reinforcement learning, where we want a robot to learn multiple motor skills, like opening a door, opening a window, closing a window, picking up an object and putting it into a bin or something. But we also, in the context of that work, we also studied some multitask learning problems in vision, where you want to learn how to predict surface normals and depth and other things from an image. And then there's also this really big benchmark called Taskonomy, I believe, built by Amir Zamir and others, that I think is, I haven't worked on it personally, but it seems like a pretty fantastic set of tasks.
Cool, thanks. Okay, so I have a question for Subotai. If sparsity really is the answer to continual learning, why haven't it been applied to RGB continual learning datasets like CIFAR or Core 50? If you increase sparsity, wouldn't that mean increasing network capacity? I.e., the bigger the sparse vector become, the more connection neurons might be needed. If so, how would that be more memory efficient than storing data?
Okay, yeah, great questions. Okay. Yeah, the first one is the easiest. We have actually applied the sparse networks to RGB data, and not just CIFAR 100. We've been working quite well with ImageNet recently, so we can, we've shown that they can train efficiently with extremely sparse networks. We're at the point now where we could start applying it to continuous learning, but we haven't done that yet. But that's definitely on our to-do list right now. So they can definitely be applied to RGB data. I think the capacity question is super interesting. And I touched on that briefly in the middle of my talk, and we published a couple of papers on it. The question, so in our sparse networks, we have sparse activations and sparse connections. So you're doing a sparse matching. And in that scenario, it turns out that as you increase the dimensionality, the system, the space grows so fast that you can actually have sparser and sparser vectors representing patterns, and up to almost ridiculous numbers. And in other papers, we've kind of shown it matches how the brain represents things pretty well. But it's actually can be more efficient if you are efficient in your storage, so that you only store the non-zero items. So if you just look at the number of non-zero components you need to recognize patterns and store patterns, as long as your dimensionality is high enough, you can get by with very small number of actual non-zero entries. And it's a pretty remarkable property of high dimensional sparse vectors. And it gets to this concept I was alluding to earlier, that the space between these representations grows really, really fast. And so what can happen is, if you, let's say you have a 500 dimensional vector, and you're storing with ReLU, it's like 50% sparse, so you're storing 250 numbers out of that 500. That's the pattern that you that you remember. If you could make that dimensionality 10,000, you can actually store much smaller than 250 non-zeros. So you can get by with less than 50, sometimes less than 30 non-zero elements. So if you look at the actual number of non-zero elements, it's actually way more efficient, even though the conceptual, the size of the system is much larger. You never actually need to store all that. You just need to store the number of non-zero items. And that's one of the tricks we think the brain uses to be able to have an extremely high capacity with a very small number of synapses or connections that are actually active for any particular task. So it's a really interesting property of high dimensional sparse representations.
Okay, thanks. Okay, I have one for Chris. So right now, the way we study continual learning, we go through this stream of tasks, and then at the end of the of all these tasks, or at the end of the life of the algorithm, we ask it to be good at everything it's seen in its life. So is that the way we should really study continual learning, or should we more study it with like areas under the curve within the life of the algorithm, which would be more aligned with what we would want from an algorithm when we deploy it in the real life to continually learn?
I'm not 100% sure I understand the question. So
I can rephrase maybe.
Oh,
it was long.
Sure.
So right now we look at, I go through MNIST and I ask the model to be good at everything it's seen in its life. So if it's analogous to me asking you to be good at an exam you took 20 years ago, basically. So is that how we should study continual learning, or shouldn't we try to maybe accumulate rewards throughout the life of the algorithm so that it's good when it's actually solving a task, and when it's not solving that task, it can overfit the task it's doing right now?
I don't know. I mean, it's an interesting question. So, I mean, a lot of the research we do in this space, especially in the supervised continual learning world, is asking the question, how can we, assuming that you don't have the ability to do full replay and store all your data and do that, how can we ensure that a system gets as close as possible to an offline system that's been able to loop over the data a bunch of times, see it in all these different orders? In this scenario you described, I don't know if that's, so it sounds like you would be okay with catastrophic forgetting. You're like, well, you're fine to forget all those earlier tests, never need any of that information again. But this future stuff, I want to be good at whatever I'm currently doing. And I don't know if that's the right thing. I mean, that may be something we already have solved. That would be like purging. I'm not 100% sure I understand the question, but based on the way you described it, my interpretation was, so you learned task 1 through 10, now you're learning task 11. Do tasks 1 through 10 even matter anymore, besides hopefully helping some forward transfer for task 11? Is that accurate? Is that inaccurate?
Yeah, and to come back on a previous point you made, you said that then catastrophic forgetting wouldn't matter, but in some sense it would, because if you forget previous stuff, it will take longer to learn these new tasks, because they're also they're related tasks. And also, if you have task revisiting, then whenever you come back to the previous task, then you could relearn it much more faster if you didn't forget it completely. So
yeah, now what? I'm still not. So in that world, what you still need to solve catastrophic forgetting. So you don't know what task is going to be useful in the future. So you learn task 11, you want to be really good at it. I mean, in one setting, you're like, well, I want to use everything I learned from task 1 through 10, hopefully provide some forward transfer. Probably not that much using most of the systems people use today. But then you don't know which of tasks 1 through 10 or 1 through 11 or 1 through 10 might be useful in the future. So I don't know if you can afford to lose them if they might be beneficial to the agent for something it might need to do later. So I don't know if we're totally missing the point. I will agree that we don't think about forgetting enough. So we worry a lot about catastrophic forgetting. But what is intelligent forgetting? What should we forget just because it's no longer helpful, no longer useful, no longer salient? Not sure if we're really tackling that at all right now in today's world. I think Subutai in the earlier panel had some good examples of that, where the agent needed to forget something just because the environment changed. And so what it learned earlier was just no longer relevant. And even humans have this problem, right? We can preserve, retain memories we wish to forget. You know, PTSD, for example, it's one of those things that people actually study a little bit in the neural network community. Just ask the question, you know, because people want to actually forget this stuff, but they can't, and because they're kind of can't lose that information that they'd actually rather not have. So I don't know. I don't have any answer for you, but I still think that at least the way that we're setting up the problems today, you can't afford to not preserve some information from previous tasks.
Maybe I could piggyback on that briefly. There's an underlying assumption that if you were to store everything and use offline batch training, that's somehow the best you can do, and continuous learning is only going to somehow incrementally approach that. I think that's incorrect. If you think about streaming scenarios and a continuously learning system can actually be far better than an offline system. And the situation there is, again, the example I used at lunch is, you're in some environment that you've gone through repeatedly thousands of times, and now one single thing changes in a real world environment, and you want to learn as quickly as possible what that specific change so you can adapt to it. If you were doing an offline system, it would take you hundreds or thousands of repetitions of seeing that thing before it becomes a significant percentage of the batch that is treated as signal instead of noise. Whereas in a real scenario, that, okay, this part of the environment changed. I need to react really fast. I need to remember that and adapt to that. And so an offline system would never be able to do that. A batch system wouldn't be able to do that without any concept of recency or temporal importance or streaming scenarios or concept of time. So I think, I don't think we should just assume that offline is the best possible system.
Agreed.
We probably need more benchmarks that incorporate a phenomenon like that. I mean, today's benchmarks don't have anything like that, right? Especially in the computer vision community. This is workshop attached to CVPR. It's like, learn all the objects in ImageNet. Great. And then we're going to test on all of them. Great. So there's nothing like that where it's like, this was irrelevant. It no longer matters. The world changed. There's nothing like that. The environment is basically still kind of stationary. It's just your experience of the environment. The agent's experience of the environment is non-stationary. So
benchmarks would be great in this area. Yeah, benchmarks would be great in this area with metrics that specifically measure these things. Yeah.
Okay. So sadly, it's already past 8, and I don't want to steal too much time from the poster session out of respect to the authors. So I think that we should cut it like this. This was really fun for me. I hope it was for everyone. Thanks for the panel again. And if some people want to say thanks as well, you can unmute and say it. But if not, have a great end of the workshop. There is still more stuff and posters. So thank you again, panel.
That was great. Thank you.
Thank you.
Thank you,
Thank you,
everybody.
guys.
Bye.
Yeah, super fun. Thank
Bye.
you.
Thank you.